And good afternoon, everybody, and welcome to today's Tech Talk on importance of industrial grounding. Nippon briefly introduced me. As he said, it's Mike Ramlachan. I'm going to be a presenter today. I'm the lead technical sales specialist here at GE Grid Solutions on all technical application issues as it comes to our protection and control platform and products. I currently reside in Orlando, Florida, which it's about low 80s today, so it's a very nice day today up there, down here. Sure for the guys in the north or gals in the north, it's probably the opposite. But today's agenda, what are we going to be talking about today? We're going to briefly go into why is grounding important. As with any presentation, we always want to start with the why. Why are we talking about this topic? And then we're going to get into the various grounding methods or methodology that we will experience or see or design into our industrial applications or industrial systems. We will do a deep dive into generator grounding because that's one of the more important assets in the industrial side besides transformers. And we'll go into not only what type of groundings do we use on different types of generators and methods that we use for grounding generators. We go into a deep dive into what kind of fault protection would we use for those various types of grounding. And specifically, what we'll be talking about high impedance grounding and low impedance grounding, and how do we protect for those two different types of grounding methods. Of course, we'll conclude, and then we'll take some question and answers at the end. So the why. Why is industrial grounding important? Why is grounding important, especially in industrial facilities? And why do we need to talk about it? Grounding provides improved safety by allowing detection of faulted equipment. It also stops transient overvoltages, especially notorious in ungrounded systems. In ungrounded systems, when you have a phase-to-ground fault, the faulted phase becomes your neutral or your reference. And the unfaulted phases then get elevated to a phase-to-phase voltage. So you're going to stress your insulators on an ungrounded system for a phase-to-ground fault to the phase-to-phase voltage levels. You want to also be able to the ability to detect ground fault before a multi-phase fault. So when a ground fault happens, you want to be able to detect that ground fault immediately and to either cause an alarm or cause a trip, and before it evolves into a multi-phase fault. Because once it evolves into a multi-phase fault, then we go into issues of damage to the equipment, permanent damage might happen to equipment, and safety issues. If the impedance is introduced, we can limit ground fault current and the associated damage that these ground faults can cause. Basically, in that case, we're going to be engineering the ground fault. We're going to be engineering the level of ground fault that we introduce into the system. Finally, it provides ground source for other system protections, other zones supplied out of, for example, if we're talking about generator, transformer, the zones that are outside of those zones of protection. Let's first talk about an ungrounded system. There is no fault current when you have a phase-to-ground fault because there's no path to ground. There might be a limited amount because of our stray capacitance to ground, but it's going to be very, very small and it's going to be undetectable. So we're not going to be able to provide ground fault protection with overcurrent relays because the ground fault current is either non-existent or almost undetectable. But if a ground fault happens, we don't want it to evolve into an unlikely scenario, but the probability is there that it might happen, that fault then evolves to a multi-phase fault because we're going to be stressing our insulators, we're going to be stressing some of the equipment because they're going to be subjected to overvoltages, transient overvoltages, and that might cause other issues and cause a multi-phase to ground fault. And then once that happens, it can cause massive amounts of fault current to be introduced into our system. So we go from zero fault current to lots of fault current, and that can cause damage to equipment, collateral damage to zones of protection outside of the equipment zone. And we want to avoid these things. But what are the advantages of having an ungrounded system? Well, if we do have a phase-to-ground fault, if our insulators are designed to handle those elevated phase-to-phase voltages, we can have a continuously operating equipment. We don't have to take the equipment down. So it basically allows us to continuously operate our process equipment, even if we have a phase-to-ground fault. So that was one of the advantages of having an ungrounded system or a high impedance grounded system, which we will discuss a lot about today, is that we can run our process continuously without necessarily having to take it down if we have a phase-to-ground fault. Obviously, eventually you would have to take it down when we don't have to take it down in an emergency situation. So how do we add ground sources? There's a couple of ways to add ground sources, but what does a ground source do? It provides a path to ground. So the impedance to ground, once it's introduced, if we can limit the ground fault current because it's an impedance to the fault, so we can engineer the fault, and hence we can minimize the associated damage that the fault can cause. We can provide ground source for other system protections, other zones supplied outside our protection zone, and it makes it easy to detect ground faults because now there is actual ground fault current flowing, detectable ground fault current flowing, because we've introduced this path to ground. So how do we introduce, what are the methods or scenarios that we can introduce a ground in a system? One is to solidly ground the system. So especially if you have a transformer, you have a Y winding in transformer, we can solidly ground that Y winding. However, once we do that, we introduce high ground fault levels because once we get a phase-to-ground fault, there's no impedance or hindrance for the ground fault current to flow. So now we have high levels of ground fault current, which we can easily detect because overcurrent relays will easily detect those high fault currents. However, as mentioned previously, if we allow ground fault to go face-to-face, the same thing with a solidly grounded system is, since the ground fault currents are high, it can cause permanent damage to the equipment and even collateral damage. And of course, the safety concerns, once high ground fault currents start to flow in our system, depending on our ground mat design, we can have safety issues of step voltages, the ground potential rise, and somebody steps on two different areas with your left foot and your right foot, you could have a potential difference between those two and allow current to flow, and that can cause a safety issue because now that personnel has experienced a shock during a ground fault event. And so what we want to do is we want to introduce grounding transformers instead of solidly grounding the system. What a grounding transformer does, it applies a low impedance or high impedance to ground, depending on our scenario that we need. So one of the techniques is to introduce the grounding transformers. Can be low impedance grounded or high impedance grounded. It provides a ground source for all faults within the system, and it allows the designer to engineer a maximum ground fault current. And why it allows us to engineer that ground fault current is because of the reflected impedance across the transformers, we can basically engineer how much impedance that transformer or system is grounded through that grounding transformer. So if we put a resistor on the secondary of the grounding transformer, we can then manipulate the winding ratio of that transformer, select the winding ratio of that transformer to effectively reflect that resistance from the secondary to the primary side, and hereby engineering our impedance to ground and such engineering our ground current. The other method is to put an impedance to ground in our transformer. So we're grounding the main transformer neutral. It can be, again, just like the grounded transformer, it can be low impedance or high impedance, depending on how we want to protect the system. And in the UK, they use these resonant grounded or Peterson calls, just for information. It's not used here in North America is much. I do see it in a couple installations, but we will not talk or focus on this type of grounding. The types of generator grounding. So one of the more important assets within our industrial system is the generator. How do we protect this generator? How do we ground this generator so we can protect it properly? So if we low impedance ground it, it provides a ground source for the system. It can get expensive, however, because we then have to have our resistor that is going to be rated for the ground fault current that it's going to be subjected to during a phase to ground fault. So we might need, the watt rating will be something that we need to design, and it can get very expensive depending on the rating of that resistors. For low impedance, as with a solidly grounded system, if there is a ground fault or especially internal ground fault in our zone, it can cause internal permanent damage to the equipment. And we're talking about, especially for a generator, it doesn't need a lot of ground current to cause faults and internal damage and permanent damage to the equipment. So when we're looking at low impedance to ground, this can be for a couple of hundred amps to a couple of thousand amps, depending on the type of resistor that you use. Obviously, if you're going to put a resistor there, you want to be in the more low side, because for a couple of hundred amps, the watt rating of that resistor would be more practical to be able to install that type of resistor. If we engineer it such that our ground fault current is in thousands of amps, then it's going to be impossible for us to get a resistor rated for that amount of energy without damaging the resistor. So typically, when you have a low impedance grounded system or a low resistance grounded system, you'll see ground fault currents typically in a range of 400, 600 amps, in that range. Even less, maybe 200 to 400 amps. So in summary, the low impedance provides the ground source, can get expensive because of the selection of the rating of the resistors, and the generator will be damaged on an internal ground fault, permanently damaged on an internal ground fault. The next and one of the popular grounding method, especially for larger generators, medium to high megawatt rating, will see designs for high impedance grounded, because that's going to be our more important asset in the station, and we don't want to subject it to large amounts of ground current. We want to engineer it so that when there is a phase to ground fault, we can easily detect that phase to ground fault, and at the same time not damaging the equipment. So typically what we do, as I mentioned, is we use a grounding transformer. And as I previously mentioned, depending on the selection of that resistor and the winding ratio of that transformer, that secondary impedance gets reflected to the primary, and we can then engineer that ground fault current. It's typically used when the generator is connected to a GSU, or a step-up transformer. So the ground source is a generator step-up transformer. And it uses principle of reflected impedance, as I mentioned, within the grounding transformer. And the generator damage is, the important thing is the generator damage is minimized or prevented actually from a ground fault. So we can easily detect the ground fault. We'll talk about next, in the following slides, is how do we protect for this high impedance fault? Because as I mentioned, when you have an high impedance grounded system, the ground fault current is going to be almost undetectable to certain overcurrent protection elements. So we need to use alternate protection elements to be able to protect a high impedance grounded generator. The other type of grounding method is the hybrid grounding, and it's a combination of low impedance and high impedance ground methodology. So here, normally when the generator is operating, this switch, it's a high-speed switch, is closed. So normally we have that low impedance ground in service, that resistor in service that's rated properly for engineered ground fault current. When we do have a ground fault, we can detect it with all of our current-based method, like our 87 or generator differential, or our 51G, or any type of ground fault overcurrent detection system, because as we mentioned, once we select the right resistor there, we're going to engineer that ground fault so it's going to be detectable by our ground protection systems. However, once we've detected that ground fault, what we do is we open up that switch, very quickly open up that switch. So then we introduce the high impedance ground into the circuit. So it's a combination of low impedance and high impedance. So as soon as we detect that high ground fault, we do not subject the generator to that ground fault for long periods of time. We open it up and then we introduce the high impedance circuit, which then limits that ground fault current. So what we have when we talk about multiple generators connected to the same bus, are referred to as bus-connected generators. There is no transformer between the generator and the system bus. So these are typically low grounded for selectivity on internal ground faults, because we want to be able to detect not only a ground fault, but where that ground fault is. If for a high impedance and ungrounded system, as we'll talk about, we can detect the ground fault, but it's not necessarily going to tell us where that ground fault is. For a low impedance system, not only are we going to be able to detect the ground fault reliably, but we're going to be able to fault locate, know where that ground fault is. When we talk about bus-connected generators, but sharing the GSU, sharing the same GSU, it's the same scenario we talked about. Is we would typically this would be a low impedance grounded for selectivity during internal ground faults, because we want to make sure that we detect that ground fault, and we want to make sure we know where that ground fault is, that we take the right generator out of service and prevent a fault on one equipment, like generator on the left, from causing damage to the generator on the right, so causing collateral damage. So this is the typical generator installation, especially for medium to large generators, is the unit connected. So as a generator would be connected to a generator step-up transformer, which is a delta on the generator side, so it's ungrounded on the generator side, and it's a Y on the Y side grounded. So our system side, it's a grounded system. However, on our generator side, it's an ungrounded system. And then we introduce a grounding transformer to make that ungrounded system a high impedance grounded system for damage minimization and for continuous process uptime. So if you do have a ground fault here, we can continue running our process until we're ready to take that process down, or that generator down, for a service to address that ground fault. So let's talk briefly about ground fault protection and detection, specifically on low impedance and high impedance systems. So as I mentioned, ungrounded on high impedance systems, there is no ground fault current, or very limited ground fault current. Especially on ungrounded systems, there is actually the ground fault current, as I mentioned, is not going to be detectable. So how do we really detect a ground fault if we're not going to have enough current available to be able to detect it for high impedance and ungrounded systems? The alternate is we have to use voltage, because that's the only other method or measurement that we have in our power system. And specifically a zero sequence, or what we refer to as a broken delta. There's two ways of getting this. One is from the broken delta connection of a three-phase VT. So we connect the three-phase VTs on the secondary side of delta, and we open one end of the delta, and we connect that to a relay. The second method is to, especially for modern microprocessor relays, we connect all three-phase VTs into the relay, and the relay then calculates the zero sequence voltage. So there's two methods. One is measured and one is calculated. So the more popular method today, because we have modern microprocessor relay is used to calculated from the three-phase voltages, whereas back in when we only had electromechanical days, the broken delta was the only way we had of connecting that to a voltage relay to be able to detect zero sequence. When you have a phase to ground fault in an ungrounded system, you're going to, as I mentioned, you're going to have elevated voltages on the unfaulted phases, face-to-phase voltages on the unfaulted phases, and you're going to have zero voltage on the faulted phase because that voltage is now grounded. So what's going to happen, I'm going to have a high level of zero sequence voltage, so I can easily detect that. In a normal balanced power system, my zero sequence voltage is 0. Because my phase A, B, and C voltages are balanced and 120 degrees out of phase with each other, and the magnitudes are pretty much the same. So when I do this measurement, this calculation for the zero sequence voltage, it will be 0. But we still have the problem of detecting where that ground fault is. If I have a zero sequence over voltage, it just tells me I have a ground fault within my system. It doesn't necessarily, it will not tell me where that ground fault is. And of course, then we use current to detect ground faults, and this is for the low impedance and solidly grounded systems. This is pretty much what we use in most installations where we have motors grounded, impedance grounded systems, solidly grounded systems. And there's two methods of measuring the ground fault current. One is to the right on this picture where we have the three-phase VTs connected into the relay, and they're residually connected to the ground input in the relay. So what does that is referred to as the measured ground current or the residual ground current, where basically on a balanced power system, A, B, and C phase currents, as I mentioned for the voltages on a balanced power system, they're when you add them up to get your ground fault current, on that residual connection, there would be 0. However, if you have a phase to ground fault, then you would have current flowing into that residual connection or that ground connection. The drawback of using this method is my accuracy and my sensitivity of my ground fault protection is only as good as my phase CTs. And what do I usually size my phase CTs for? I size them to detect phase faults, which are usually large fault currents. So they're usually size higher, and the accuracy, because they're size higher, especially with protection, the accuracy might not be there. So when I'm using this type of connection for ground fault detection, I got to make sure my ground fault is going to be pretty high, and the accuracy is not going to be a concern. However, as we talked about, when we're engineering like low impedance, when we're engineering the ground fault current that we engineer, we want it to be low, so that in our residual connection, we might not be able to detect it reliably. So we use what we call as a ground current CT with a zero sequence connection. So basically what we do is we have that ground CT, and all three phases of the conductors go through the hole in that CT. So the output of that CT is the addition of those three phases, and hence we get our ground current. In a normal condition, again, in a balanced condition, there's no ground fault current flowing. However, when we do have a ground fault, the CT is going to be sized so that it's accurate and that it measures very low ground fault current. So the disadvantages of using this is that those conductors that we have to fit through the hole in the CT, depending on the size of those conductors, we might have to have a large enough hole for those conductors. We will have to have a large enough hole in the CT for those connectors to go through and fit through. So let's talk about, we talked about the various grounding methods for generators, and let's talk about how do we protect for those various grounding methods in the generator. So what we're going to be first talk about is a high impedance grounded, which we mentioned is usually through a grounding transformer. And we talked about previously that since In high impedance or ungrounded systems, since there's no detectable ground fault current flowing, we have to use voltage. In this case, the overvoltage element. So the overvoltage element is basically measuring the voltage on the neutral. So that gets hooked up to our relay, or we can calculate it from the three-phase VTs, as we mentioned. The issue with the 59N here, it's not going to provide us 100% coverage for faults within the generator. When we talk about 100% coverage, when we look at fault at the terminal, that's basically 100%. Then the fault at the neutral of the transformer, that's 0%, because the fault at the neutral is effectively just another ground within the same ground, and you're not going to get any ground fault current. So with the 59N is because of the accuracy of the relay, accuracy of the VT that we're measuring, especially, we're not going to be able to reliably detect for ground faults close to the neutral of the transformer. It might give us very good coverage for about 90% of the generator, so the terminal, from the terminal voltage to about 90 to 95% to the neutral of the generator. So what do we do for that additional 5 to 10% coverage? What we could do is 27TN, which is an undervoltage third harmonic element, and we'll talk a little bit more on the following slides on that. Or we can also use a 59D as a 59 differential, which looks at the neutral voltage and the calculated zero sequence voltage from the terminal voltages of the transformer, and we do a differential between those two voltages, and if there's an internal fault, then that differential will be non-zero, just very similar to a current differential system. So I mentioned the 59N element, so it's a linear distribution in terms of the amount of voltage that we're going to measure from the fault position or where the fault is. So at the generator terminal, it's going to be very high voltage that we're going to measure, whereas if faults close to the neutral is going to be almost undetectable, especially in the last 5%. Usually what we have is two of these elements, a high-speed element. So for faults very close to the neutral of the generator, we can trip very quickly for those faults. However, for faults that are closer to the neutral of the transformer, we might want to time delay that, because allow other system elements to clear first, because for ground faults in other parts of the system, it might look like an internal ground fault to this element. So we need to coordinate for those types of faults. So we might have two stages. Stage one, a high speed, which might be set like 50% or above, and then stage two, which is a time delay, which can be set for less than 50% for coverage. The third harmonic. So third harmonic is generated in a generator when it's running. It's always some third harmonic current voltage present in the terminal and the neutral. And that distribution of third harmonic is pretty linear from the neutral up to the generator terminal. We could use that to be able to detect if there's a fault, because if there's a fault, the ground fault, the voltage, the neutral voltage will either, if there's a fault to the terminal, it will drop to 0 from a high positive number. If it's a fault on the neutral, it will drop to 0 from a high negative number. So we can use an undervoltage third harmonic or 27TN element to be able to detect ground faults within the generator. As I mentioned, that gives us that additional 0 to 15% coverage that we might not get out of the 59N element. And the 59D element, the third harmonic differential or ratio voltage, as I mentioned, takes the measurement of the transformer neutral, compares it to the calculated voltage measurement from the terminals, and it does a differential between the two to detect that it's an issue within the generator, a ground fault within the generator. One thing with the 27TN, it's very difficult to set this 27TN, because first we got to know what levels of third harmonic are present when the generator is running. And there are cases when the generator is running certain power factors, certain load pockets where that third harmonic voltage will fluctuate, might even drop to 0. And that can cause a misoperation of that 27N element, so 27TN element. So that you need to take that into consideration. Whereas the 59D element, if you use the third harmonic ratio voltage, we're not basically subjected to those pockets. We might not be able to trip for ground fault because there's not going to be third harmonic generation, third harmonic voltage generated, but we're not going to be able to detect the ground fault either. So it's more secure. So basically, for this voltage type protection for high impedance grounded transformer is a combination of the 59N, the 59D, and the 27TN to give us 100% overlapping coverage for ground faults within the generator. The last method we're going to talk about is a subharmonic stator ground fault, or the injection method. Basically, this is a method where we couple an injection set to the grounding transformer, which is coupled to the neutral of the generator. We inject a low frequency, a subharmonic frequency signal in the generator, and we measure the resulting current. If the generator is not faulted, it just has the straight capacitance and surge capacitance, the currents that we're going to be seeing are reactive only, right? Or capacitive reactive currents. Whereas if we do have a ground fault within the generator, we'll see a high level of resistive fault current. So that's what this set is doing. It's injecting the voltage. We read the resulting current with our relay, and that relay then extracts the resistive component to that current. And if that resistive component is pretty high, then it's going to trip and say there's a ground fault. For low impedance machines, we have 3 different techniques that we usually use. The 50 overcurrent element, the 51N neutral overcurrent element, the 67N, the neutral directional overcurrent element, and the 87GD, which is a ground differential element, very similar to the 59D that we talked about, the third harmonic differential element, but it uses current instead. But since for a low impedance generator, we have enough fault current that we're engineered, we're going to be able to use these methods for high impedance or low impedance grounded machines. So we'll talk about why the 67 versus the 51N in the following slides. So with the 67, especially when you have a bus connected generator, or as we mentioned, generators connected to the same bus, it's going to be difficult just with the 51 element to fault locate. So if the fault is on the adjacent generator, both of these 51N neutral overcurrent elements will pick up and trip for that fault because they're seeing the same fault currents. Whereas if we use the 67N, the 67N only looks within the into the generator. So if we have a fault out in the system, the ground fault system is detected by the 51 element, so that if we do have a fault in the system, we still want to trip our generator if that fault is not cleared in time. We don't want to cause damage to our generator, but we also want to allow the system protection to trip that fault first. So we coordinate with this 51N for external ground faults. However, we have an internal ground fault, then the 67N element, which is looking only in towards the generator, will trip for that fault. And not only will it trip for that internal fault, it will trip for only the fault in that particular generator. So we're able to fault locate exactly where that fault is and be able to isolate that piece of equipment only. Whereas if we had the 51N, we'd probably have to trip both generators for a ground fault in either one of those. So the ground fault in the machine is detected by either the 67N or the 51N. The 51N picks up in the unfaulted machine. The 67N trips only fast on the faulted machine. Then the 51, the faulted machine, trips the 51N resets on the unfaulted machine, and we go back to normal, allowing the unfaulted machine to stay in service. For ground faults, ground fault in the machine is detected by a 5087 GN. So if you have a ground fault detection, it's the same as having the 67, where the ground differential protection will be able to follow code exactly which machine the fault's on and only trip that particular machine, and allowing the 51N to reset and not trip both machines. So as with the high impedance ground fault protection, we can look at the various methods to protect for a low impedance grounded machine. And we notice that all of these methods pretty much give you good coverage. It's very difficult, probably impossible, to get 100% coverage, however, because if we have a fault very close to the neutral of the transformer, it's the same thing as having, is bypassing that grounding resistor. So you're basically bringing that ground up to the ground of the transformer, and you're not going to be able to detect that because it's not going to be any ground fault, right? So it's going to be very low or close to zero ground fault current. So for that last couple % of the generator, you will not be able to reliably detect to give you 100% coverage. And that might be okay because, you're still continuing with your process. If there's another ground fault somewhere else in the system, then you get a phase fault and you'll be able to detect that. However, obviously you risk collateral damage because now your two ground faults give you a phase to ground fault, phase to ground fault if it's on a different phase, and you can cause other high fault currents to flow in your system and cause other issues and collateral damage. So in conclusion, we talked about the various methodologies for grounding. So we thought grounding is very important for safety and for equipment protection. Depending on the ground fault that we use, we can engineer ground fault current, and the protection will depend on the grounding method. So we talked about the high impedance grounding method, where we use basically the voltage or the injection method to detect ground faults within a high impedance grounded generator. Then for low impedance grounded system, we talked about the various overcurrent methods that we could use. The 67N is to fault locate only in the faulted generator, as well as the 87's ground, or the ground differential, is to fault locate only on that low impedance grounded generator where the fault is. So it gives you the ability to segregate where that fault is and only trip the equipment that's faulted. And then we have typically the backup 51N, which protects you for system faults that might cause damage to your generator, but you might coordinate with those fault currents because you want the system protection to trip first. But if it fails to trip, then you want to trip your generator. Also, it's a backup protection if your 67N or your 87N fails to trip. In the high impedance method, we talked about a couple of voltage methods. One is just measuring the zero sequence voltage or the neutral voltage of the transformer, and it's an over voltage. So if we have a ground fault, the zero sequence voltage will be elevated because the faulted phase will be zero and the unfaulted phases will be elevated. So we can easily detect that if the fault is not close to the generator neutral. If it's close to generator neutral, we're not going to have enough zero sequence voltage developed to be able to detect it. So we need another method of detecting for faults there. And that is the 27, the third harmonic undervoltage element. As I mentioned, when a generator is normally running, there's third harmonic voltage being generated. And we can use that to set our 27. But it's difficult, as I mentioned, to set that 27 element, TN element, because we need to know the levels of third harmonic. And it can change during the loading, power factor scenarios, the various load pocket, load conditions, system conditions of the generator. That third harmonic voltage will change. So in certain cases, it could change where it gets very low and it could misoperate our 27 TN, thinking there is a ground fault when it's actually the generator operating in a pocket where the third harmonic voltage is very low. So we can then use the 59D element, which is the third harmonic differential element. There's a ratio looking at the third harmonic from the terminal of the generator to the neutral third harmonic voltage of the generator. And we can detect the ground fault using that method, and it will not be subject to misoperations like the 27 TN. It might be subject to where it will not be able to detect certain types of ground faults, especially if the generator is operating in a low pocket where we have low third harmonic voltage. So if we have low third harmonic voltage, the voltage differential, depending on the pickup setting, might not be able to pick up for a ground fault in that region. So it's more secure than the 27 TN, but it's not completely dependable. The most dependable method is the injection method, which gives us 100% protection, ground fault protection within the generator, where we inject the voltage, subharmonic voltage in the generator coupled grounding transformer, and we measure the resulting current, and we look at the resistive component of that current, and we can determine if there's a ground fault in the generator. This method is very advantageous in that it doesn't matter what load pocket the generator is running, we'll be able to reliably detect the ground fault. And not only when the generator is running, but when the generator is not even running, we can still inject that that subharmonic voltage and be able to detect ground faults even when the generator is not running. So it gives us a heads up before we start running the generator. Hey, there's a ground fault already on there. We need to look at it before we start the generator. The only one disadvantage of using it is when the generator is getting up to speed, there might be a period where the generator is at the same frequency that the injection set is injecting in. So at that frequency band, we might have to block the element from operating. But that's, as I said, it's a very low, it's about 20 hertz, so you don't expect the generator to be operating in that region for very long. It's, when it's getting up to speed, it should be go through that region fairly quickly. So in conclusion, multiple protection elements are required for the various types of grounding method. We talked a lot about all those various methods. With that, we can start to take some questions. So one question is, question number one, what neutral resistor is chosen for high impedance grounded machines? So that's a good question. When we engineer our ground fault or we engineer our grounding transformers, what resistance do we want to use? So the neutral resistor is typically chosen such that the power dissipated in the resistor during a single line to ground fault is approximately equal to the reactive power produced by the zero sequence capacitance of the stator winding and the generator's step-up transformer low voltage winding. So you need a couple of pieces of information, that specifically the zero sequence capacitance of the stator winding. You might or might not have that information. That might need to come from, when you're designing your generator manufacturer, when they're designing the generator. It could be empirically calculated. I'm not sure if there's a method to actually measure it, but that's one of the components you'll need to determine that neutral resistor. So let's take the second question is, one of the questions, okay, so I was looking at the pre-registration questions that you guys have submitted, and one of those questions posed prior to this seminar in the registration process was, what are the various types of grounding methods that are used in industrial environments? Well, I hope that this seminar gives you an answer to that. We talked about that specifically in the seminar, the various types of grounding methods. Like we discussed and introduced the various grounding methods, which are ungrounded, solidly grounded, low impedance, and high impedance grounded. Obviously, there's a lot more that we can provide in this hour that we have together. However, I hope that the seminar at least gives you an introduction into those various methodologies, not just the methodologies, but what are the advantages, disadvantages, the various ones? Why do we use one against why do we use the high impedance versus the low impedance. And then we talked about how do we, once we've selected the type of grounding method for our system, how do we protect it? What are the various methods of protecting the for example, high impedance grounded system or low impedance grounded system? Specifically, we talked about as it applies to generators. So the third question is, we'll take is, does high impedance grounding have a practical significance at industrial facilities? So I would think, based on our discussions that we had is yes, right? It provides the maximum service continuity. We don't have to stop the process immediately. We could take the process down whenever we need to. We can keep the process up because we're not subjecting the machine to large amounts of fault current. There's basically no ground fault current being introduced. It also controls the transient overvoltages due to arcing during ground faults on ungrounded systems and relieving stresses placed on the insulators, which might or might not be designed to handle those phase-to-phase voltage stresses. We can locate ground faults when they do happen with the various protection measures we discussed, from the voltage methods to the current methods, depending on whether it's high impedance or low impedance. Okay, continuing on here. One of the questions here, Nippon, I'll leave you to answer this at the end of the seminar, is what will we get the slides of the presentation? I believe the answer is you can replay this I'll leave Nippon to answer that at the end. Fourth question here. I see a couple of questions. Again, here I'm looking and I see a couple of questions here that I can lump into one on ground grid design to control step and touch potential. Yes, this is certainly a huge safety concern to personnel during ground faults when the ground potential rise can cause significant step and touch voltages or potential, which we refer to as ground potential rise. In addition, the ground potential rise can cause issues with secondary systems if they're not grounded properly. For example, in a CT circuit, it's usually you have one safety ground, which is usually in the residual connection of the CT on that CT circuit. If you, for example, mistakenly apply two grounds, or during your insulator breaks down and it gets shorted to ground, and you have two grounds in your CT. When you have a ground fault, there's a ground potential rise, potential difference between those two ground points, and they can cause currents to flow in that CT, which would not otherwise flow. And it can cause issues for the protection elements that are in that CT circuit. So grounding is important not just on the primary process equipment, but on our secondary equipment. However, the discussion today was focused more on grounding methods and their protection. We don't have enough time, or didn't have enough time, to get into those sorts of ground grid design and touch and step voltages. But I just wanted to mention, yes, there are things that we need to think about and design to be able to when we are designing our ground rig and our ground system. I also see a number of questions on overcurrent coordination. Again, I talked about the 51N coordinating with the system protection, but we didn't get into what coordination is, how do we do coordination. Again, we don't have enough time in the seminar to go through all of these things. So, but I think we previously did do a tech talk on feeder protection where we did touch on or go into details on coordination. So I'm not sure, those seminars, not just this seminar, but all our previous tech seminars are available on our website on demand, as Nippon mentioned, to go back to. So if you're unable to find it, reach out to us, and I can look it up and tell you which one it is, so you can go through that particular tech talk and where we discuss coordination in more details. How can a protection function see in a certain direction? Example, i.e. the 67N. That's a good question. Again, Not something that we were able to get into today in details, but again, there's another tech seminar that I could refer you to where we did talk about 67N. I think it's the same seminar where we talked about coordination protection, actually. But you need two components when we're talking about direction. You need an operating quantity, which is our current, and then we need a polarizing quantity to tell us what direction that current is. And typically, our polarizing quantity is our voltage. So basically what we do, we need the voltage and the current that goes into our 67N relay. And that relay then looks at the angle difference between the current and the voltage. And based on that angle relationship between the current and voltages, it can tell if the fault's in the forward direction or the fault's in the reverse direction. If the fault is in the forward direction based on that angle relationship, and the overcurrent element has also picked up saying that there is a fault level, a fault current level that's high enough to pick it up, you need both of those two to operate the 67N. So I hope I did that explanation some justice there, but it's better when we have pictures to explain how do we look at those angular differences. There's another second method of second polarizing quantity methods where we don't use the voltage, where we use a current. And that would be, for example, if you have a transformer, we would polarize with the neutral current of the transformer to, for example, the neutral current of the feeder. So if the fault's in the forward direction, we expect the angle between the neutral current in the transformer and the angle of the neutral current in the feeder, we expect that to be within phase with each other. If the fault's in the opposite direction, we expect them to be out of phase. So that's another polarizing quantity, the neutral of a transformer. So another question, aren't resistors also time rated? Yes, I mean, they're related. The relationship is just like a piece of wire, right? It's I squared R rating, and it's time. So the longer you heat that wire up, the above its rated current, you'll eventually damage it. And how long it takes to damage will depend on the amount of current. So there is a time rating up to which that resistor, and that's what happens when we size these resistors. We make sure for the maximum amount of time that fault current is allowed to be on the system, that it's not going to damage that resistor. So as I said, it can get expensive to size that resistor properly to not only manage to carry the fault current, but to carry it in the time that we needed to carry it. That's a very good question. Okay, let me take a look here. What should the CT ratio be of zero sequence CT for sensitive earth fault in a low impedance system? Should be the same as a phase CT. Okay, so yep. So for a low impedance system, it definitely should not be the same phase, the same ratio as a phase CTs, because they're doing two different things, right? The phase CTs are protecting for a phase fault, which is going to be significantly higher than a engineered ground fault in a low impedance system, whereas the zero sequence CT is going to be detecting ground fault currents only for phase to ground faults, which are much more lower level. So the ratio might be higher than the phase CTs because you want to be able to reflect that primary current on the secondary where the relays can read it. So that ratio could be much higher, and it might be more accurate. That's what you refer to the sensitive ground fault protection usually, because it's not only can read lower levels of fault current, but it can be more accurate at those lower levels of fault current. So I'm trying to read through some of these questions here. For the generator alt fault injection method not available, then which is the best solution that can put? Okay, I'll read it back here. For the generator alt fault injection method, I'm thinking this person is probably from Europe, because in Europe they refer to as earth fault, not ground fault. So he's asking if for the injection method, if that is not available, then which is the best protection that can be used? And I'm assuming, making some assumptions here. I'm assuming he's asking about the high impedance protection, which we can use the injection method. So if the injection method is not available, and most of the times it's not, because it's a pretty expensive method, right? We need the injection set, we need the testing to go along with it, we need additional pieces of equipment and such. So if you don't have that method, then you can use a combination of the 59N, as I mentioned, the 27TN, and or the 59D method, which is the third harmonic undervoltage and third harmonic differential methods. And the combination of those various methods will give you close to 100% protection for the generator. So what that is, if I can take one more question. Hybrid ground seems to be the best protection. Why would we use any other method? And he says cost. And of course, cost is one of the most, I personally have never seen a hybrid grounded method being used in most of my travels or my career so far. I mean, I could be wrong, and I believe it's because of the cost, because you need that extra device, switching device, which needs to be certain speed, high-speed device. And then you need the resistor to go along with that, so that becomes expensive. Then you also need the high impedance grounding transformer. So the cost associated with that method is going to be significant. And not only that, it's you have to also assume worst case scenarios is if that switch fails. And if that switch fails, then you might have issues in your system, so collateral damage in your system. So people might not want to use that because it's certain amount of risk involved. I'm starting upon, we're up to the last minute there. You want to take us out?
Thank you, Mike, and thank you everyone for attending. We look forward to seeing you again. Until then, stay healthy. This concludes today's webinar. Have a wonderful day.